Okay, continuing on today with our Laplace transform playlist. We have here another differential equation. We've got y double prime plus 9y prime plus 14y equals 0. And we have our initial conditions, y at 2 equals 2, and y prime at 2 equals 1. Okay, now to get started with this, there is a problem we're going to run into in a minute, but I'm just going to start off the way we usually do and just take the Laplace transform on both sides. In doing this, I can break up the left side like we've done previously. So this is going to give me Laplace of y double prime. Here I'll take the 9 up front, and we'll have the Laplace transform of y prime here. And then this here, we'll bring a 14 out, and we'll have Laplace of y. And then over on the right side, the Laplace of 0 is going to just be 0. And so as we went over previously, we have a formula for the first derivative and a formula for the second derivative. The formula for this is going to be s squared big Y of s minus s y at 0. And then the last piece is going to be just y prime at 0. And here's the issue. We don't have y at 0. We don't have y prime at 0. Our initial conditions are at 2. So we'll keep going, but we'll come back to that in a second. But that's going to be the thing we need to deal with. And then we'll just have our formula over here for y single prime. This is going to be s big Y of s minus, distributing the 9 here, and we're going to have, this is going to be y of 0. And then this last piece is just going to be plus 14 big Y of s. And this is all equal to 0. So what we'll do, we'll factor out the big Y of s here, and then taking all those terms we're going to have here, this is going to be s squared plus 9s, and then there plus 14. And then for everything else what I'm going to do is I'm going to bring it onto the right side of the equation by just adding it. So we'll have this s y of 0, then we'll have plus y prime of 0, and then here we'll have plus 9y of 0. And then what I want to do is we want to just isolate our big Y of s, so we'll just divide by this on both sides. We'll divide by s squared 9s plus 14. We'll do it here. I think over here what I'm going to do, I'm actually going to factor it though, because this is factorable. So I can actually write this as s plus 9 times s plus 7. This will cancel here. And what we'll do is we'll take the Laplace inverse on both sides of the equation. We'll sneak it in right here as best we can. And now this big Y of s, this is just the Laplace transform of y. So this inverse will reverse it. And so on the left side, we just have y, and we've isolated it, and we just need to find this inverse Laplace transform. But now before I just go in and rewrite this, I just want to notice something here. This right here, everything here is just constant values. If we knew what those values were, this would just be some constant. And this is another constant here. So I think what I do when I rewrite this, let's just write it as we'll have our first constant, c1 times s, plus a second constant that we don't know. So we'll just write it this way, and we'll write it, we'll bring it down our denominator. But now for this thing, let's just do what we would usually do. We want to split up this denominator, so we'd use partial fractions for this, and we could try to use the cover-up method. So let's see what that looks like. Okay, so here's our setup for the cover-up method for partial fractions. We could do what we always do. We could plug in like a -2 here for s, and get a value for a in terms of the constants c1 and c2. But the thing is that value is just going to be some other constant value. It's just going to be like a more complicated constant value. So let's just leave it as a. Let's just call it a, and we'll figure it out later. And the same thing here, if I plug in -7 here, we'll get another constant value. We might be interested in these c1, c2 values, but right here it doesn't really matter. It's just some constant, and we're still going to need to figure some stuff out later. So in this case, I'm actually just not going to really worry too much about these constants. We'll break up this Laplace inverse into 2 Laplace inverses. The first one I'll write is a over s plus 2. And the second one, we'll just have this. We'll have the Laplace inverse b over s plus 7. But now we can use the same formula on each of these. We found this formula very early on. It's just the Laplace. We use the Laplace of EAT, and it's 1 over s minus a. So for this one, our a value is going to be -2, and here it's going to be -7. So writing this down, we're going to have this as a e minus 2t plus b e minus 7t. And so this here will be our general solution for y. The only thing is, what do we do now with this a and b value? What is this going to be? So let's just clean up the board and we can solve for a and b. Okay, now at this point, we're just solving it like a normal differential equation, like an initial value problem where we end up here and we have our initial conditions and we just use them. The first thing we're going to need is notice we have a derivative here. So I want to find out what is the y prime value. So we can just take a derivative of this thing, and we're going to have -2 a e to the -2t. And then here the derivative is going to be -7b e minus 7t. And then we'll use what we have here. So first we'll look at what is y of 2. So we'll take this first equation and just plug in 2. So this is going to give me a e minus 4 plus b e minus 14. Then doing the same thing here, y prime at 2, this is going to be, we'll plug in here, so we're going to have minus 2a. This again is going to be e minus 4. And then here we'll have minus 7b. And then plugging 2 in here, we have e to the minus 14. And we have our values for each of these. This is actually 2 here, and this is actually 1. So we can use whatever method we want on this. I think what I'll do is I can multiply this first equation by 7 and add it, just kind of on the fly. So if I multiply in 7 here, we have 7a minus 2a. This is going to give me 5a e minus 4. Here, when I multiply in 7 here, this term is going to cancel because we have 7. We'll have plus 7b and minus 7b, so those go away. And then on the right side, this is going to be 14 plus 1, so this is going to be 15. So I can divide by 5 here, divide by 5 here, this is going to give me a 3. So for our a value, we're just going to end up with 3 over e to the 4th. So next what I'll do, I'll take this a value and I'll just plug it into the first equation. So that's going to give me, what's going to happen is the e to the 4 times e to the minus 4 is going to cancel, and we're just going to end up with 3 here, plus b e minus 14 equals 2. Subtracting 3 on both sides is going to give me a minus 1 over here. So for our b value, we're going to have just minus 1 over e to the 14. So now from here, all I need to do to finish it off is take my a and b value over here, and we'll just plug it back into this equation and maybe do some simplification. So when I do that, let's make a little bit of space. So let's see what's going to happen. So we're going to have our y, plugging this in, we're going to have our a value 3 over e to the 4th times e to the minus 2t. So then we'll have our plus b value. Actually, I'll change this to a minus sign. So this is going to become minus 1 e to the 14 times e to the minus 7t. So what I can do is write this for my final solution. We'll have 3e4 minus 2t minus e14 minus 7t, and that's it. So there you have a differential equation where our initial conditions are not at 0. One note on this, there are a few different ways to handle initial conditions like this, but this works pretty well in a case like this. So that's it. Thanks everyone for watching. Have a great day.